Friction clutch, second part. We will be looking at the uniform pressure theory. So actually for friction clutch or disc clutch, we have two theory. One of it is uniform pressure theory and the other one is uniform wear theory. So in uniform pressure theory, we usually say that the pressure distribution on the friction lining material is being considered as uniform, and this is especially when we are referring to a new clutch. Okay, a new clutch. So if let's say for example we are referring to a clutch which has been used for a period of time, which has been worn out, okay, the pressure distribution would not be uniform anymore. So in that case we will have to consider uniform wear theory. So on uniform pressure theory, the torque transmitted by the clutch, by the disc clutch. Now first thing we look at the surface of the frictional lining material by taking an elementary ring from the frictional lining material. Okay, so we assume that the thickness of this elementary ring to be dx, and then the radius here, the radius of the ring to be x, okay, of the friction clutch plate. Now from there, okay, we have this as the force, the spring force or the normal force that is acting on the elementary ring actually. So T, we take it as the torque transmitted by the clutch. P, the lowercase letter p here, as the intensity of the axial pressure with which the contact surface are held together, being held together. R1 and R2 should be the outer radius and the inner radius of the friction lining material of a plate clutch. Now R to be the mean radius and x to be the radius of the elementary ring here, dx to be the thickness. So mu will be the coefficient of friction. As I've said, the coefficient of friction relies on the surface of the friction lining material. If it is rough, then the mu will be higher, and if it is smoother, then the mu will be lower. So now what we need to do is to find the area. That is the first thing, because we know that pressure is equals to force over area. So the pressure distribution on the friction lining material will be based on the force, that is the spring force, divided by the area. So now for this case we are taking the elementary ring. So the area of the elementary ring, the length of this ring here, we can take it as 2 pi multiplied by the radius r or x. It depends on whether we consider it as x or r. It doesn't matter. Okay, so you can consider this as x and dx, that is for the thickness, or dr for the thickness. So normal or axial force on the ring, the normal force or the axial force that is acting on the ring. Therefore, since pressure equals to force over area, so we can say the force is equals to pressure times area. So pressure for this case is considered as uniform. So we consider pressure to be a constant times 2 pi and r, that is the mean radius of the elementary ring, and dr, that is the thickness of the ring. Now considering uniform pressure theory. Okay, so this, as we know, that is the tangential force or the frictional force which is acting on the elementary ring. So if this tangential force multiplied by the mean radius will give us the torque. the turning moment. So these are the spring forces that is acting on the ring. Now, frictional force on the ring acting tangentially at radius r. Okay, at radius r. So we know that frictional force is defined as the product of coefficient of friction with normal force. I repeat again, the normal force will be the spring force. Why we are putting a delta or a D here is because we are only looking at a very small portion out from the total surface of the friction lining material. We are only referring to a tiny ring. So that is why we put delta, or sometimes we put a symbol of D, the differential form. So frictional force will be equals to the coefficient of friction, and we know that from the earlier slide that the normal force is equals to pressure times area. So this is the area, the length of the elementary ring multiplied by thickness give you the area. Okay, so pressure times area. So this is the frictional force that is acting on the elementary ring. So frictional torque. Now, how to produce a torque? So I repeat once more again. Torque is equals to the tangential force. In this case, is the frictional force multiplied by the radius. So you have this. Now, since we know that frictional force is equals to this, now what you need to do is substitute this into the Fr, so you have this mu p 2 pi r dr multiplied by this radius here again, because now you are looking at finding out the torque transmitted by the elementary ring. So rearranging the equation, you will have r times r equals to r squared. Note that when the friction surface is new, if the friction surface is new, that means if you are referring to a new clutch, there is a uniform pressure distribution over the entire contact surface. This pressure will wear, this pressure or this surface will wear most rapidly where the sliding velocity is maximum, and this will reduce the pressure between the friction surface. So let's say you have a pressure plate acting on the surface of the friction lining. After a period of time, what happens is the thickness of the plate will be reduced, or the surface will not be uniform anymore. So the pressure distribution therefore no longer exists. Okay, this wearing in process continues until the product of pressure and volume is constant over the entire surface. After this, the wear will be uniform. Okay, so for uniform pressure, we consider the pressure distribution over the entire surface to be constant. Now, from the torque transmitted by the elementary ring. Now, if you want to find the total torque transmitted by the entire surface now, the entire surface, not by the elementary ring anymore, the entire surface, what we have to do is we have to add every each of the elementary ring that exists within the surface to get the total torque that is transmitted by the entire surface. So the only thing we can do is to integrate the whole equation here with respect to r. So you have the upper limits, that is the r1, that is the outer radius, and the lower limits to be the inner radius, r2. Because you are going to add in all the elementary ring that exists between these two radii here. So that means you'll be adding from this point until this point. So starting from R1 to R2. So we know that the 2 is a constant, the pi is a constant, the coefficient of friction relies on the material, the type of material that you use for the frictional lining, and P to be considered as uniform here. So R squared dr are the variables. So integrate r squared with respect to r. So you will have r to the power of 3 over 3. And then by putting in the limits, you have r1 cubed minus r2 cubed over 3. And since we know that pressure equals to force over area, so that is the area of the entire surface of the friction lining, which is pi r1 squared minus r2 squared. So what we need to do is we can substitute this P, which is equals to this, into the equation here. So you have this P now becomes, okay, W over R1 squared minus R2 squared, where the pi has already disappeared because it's cancelled off with this pi here. When you substitute this whole equation for P, the pi will be cancelled out. So you will have 2 over 3 coefficient of friction mu, the spring force W or the normal force, multiplied by R1 cubed minus R2 cubed divided by R1 squared minus R2 squared times n would be the number of pairs of contact surface. Remember, for a single disc clutch, the number of pair of contact surface is 2. Thank you very much. That's all for this part. And please, if you have any questions or comment, please put on the comment section in my YouTube under all four clutches, all frictional clutches. Thank you very much and see you soon. Bye bye.